Hello, Mr. Fem, can you hear me? Hello. Ah, what's wrong? My mic is on, my video is on. I can't hear him too.
Because I'm backstage. Hello? Hello? Okay, now I'm no longer backstage. Hello? 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 Yeah, I am speaking. I am speaking. I'm speaking. Can you hear me? I am speaking. I
You'll be
am
able to hear me
speaking.
now.
Yes, I can hear you now.
Okay, but previously my audio was not on.
Yes, I could not hear you a moment ago.
Ah, okay. Okay, yeah, no problem. Um, maybe because of the hand spear I'm using. Okay.
All right.
But so Joseph, if you can join the screen again, let's
Okay, I should log out and join again.
okay, we can hear you now.
Hello. Hello. Um, okay. Um,
Since we have some technical issues today. Okay, no problem. So Dr. Kene, are you ready?
Yep, I am.
Oh, great. So yeah, we are actually excited to actually have you, Dr. Kene. I will quickly read his profile for us. Just a minute, please. Um, okay. So Dr. Kenechuku is a STEM educator and roboticist. He is dedicated to inspiring and educating the next generation of engineers and innovators. As an assistant professor of robotics at Franklin W. Olin College of Engineering in Massachusetts, USA, he teaches and conducts research in sustainable agricultural robotics and human-robot interaction within shared control systems. Kenechuku's passion extends to advanced robotic education and application in Africa. He leads the Pan-African Robotics Competition Engineers League and serves as the lead author for the upcoming biannual report titled State of Robotics in Africa. He holds a bachelor's degree in electrical engineering from Covenant University, Nigeria, along with a master's and PhD in robotic engineering from Worcester Polytechnic Institute. Massachusetts. And we are actually happy to have Dr. Kenechuku facilitate a section with us today on robotics, automation, and AI application in agriculture. So, Dr. Kene, you are very welcome. So I'm putting up
Thank
your
you.
screen right now. Okay.
Awesome. All right, thank you very much. Just before I jump in, I just have a few questions for you, Femi. Do I adjust the timing of my
Can
presentation?
you use a share screen?
Right.
Yeah.
Sorry. Yes, I can see this. I had a question for you. Should I adjust the timing to accommodate for the time on the front end that we've lost, or I should still work towards an hour and 15 minutes? Can you hear me?
Yeah, you're audible.
Okay, I was asking you a question. I don't know if you heard that.
You were asking me?
I was asking you if I should adjust the time for my presentation to account for the about 15 minutes that we may have lost on the front end. Just to know
No
how I
worries.
should move through the presentation.
I think that the time is down, so it's
This
all
time
yours.
is still fine? Okay.
Yeah.
All right, so let me put this in presentation mode just to make sure that's coming through. Okay, looks good. All right, thank you very much. It's a pleasure to be with you all. I cannot see who is engaging with this event today, but I guess at some point there might be some interaction. It's a pleasure to be invited to talk about robotics, automation, and AI in agriculture. And I'm very excited to be here. Thank you to Precision Field Academy for the invitation to be here, and to Mr. Femi as well. So I'll start with a brief intro about myself. As was said in the citation, I am an assistant professor. I teach robotics. I do research in robotics in an engineering school in the US. A bit about my background: I grew up in Lagos, Nigeria. My undergraduate degree was in electrical engineering, and then I came to the US to do my graduate studies, both master's and PhD in robotics, and that has sort of shaped the direction of the work that I do since. During my PhD, I did work in human-robot interaction for semi-autonomous vehicles. So I did some simulation of how drivers interact with vehicles that have some level of autonomy. But then since I've moved my research interest in the space of sustainable agriculture using robotic technology. So the image you can see here is an autonomous tractor that we were, or an existing tractor that we converted to have autonomous features by a couple of students in my school year. And then beyond research, I'm very passionate about advancing robotics in Africa. I think has been mentioned, I do that through the Pan-African Robotics Competition that I would like to invite those of you who are really interested in robotics to consider participating in. I might talk a little bit more about that towards the end. All right, so I will start off with my talk generally. One thing that I want to start off by mentioning, though, is I would like this to be somewhat interactive. I don't know what modalities for interaction is existing with this platform. It might be through chat or through question and answer through chat, but anything that's possible, I would like to definitely get some feedback from people as much as is possible. But anyways, I'd like to just maybe, share this thought about what is farming today. And there are a couple of images you can see on the screen. Hopefully these images are somewhat familiar to you, farming using mechanized systems like tractors that can do multiple things on the farm, being operated by a driver or a farmer who is driving the tractor. On this other image, you can see people doing harvesting of different vegetable crops, and then also livestock farming. This is very common in Nigeria, particularly in northern Nigeria, where you have herders who would take their crop around to graze and to drink and to migrate around towards where there's pasture. But an important question for us to consider, not just farming today, but what is farming of the future? All right, that's probably more relevant, more crucial. In particular, farming of the future in 2050. Okay, so or 2100. It's hard, at least for me, it's hard for me to imagine that 2100 is coming, but it is here. It's going to be here in less than 80 years, in about 70, 75, 76 years. Yeah, 75, 76 years. We would be in 2100. I might not be there to see it. Some of you might be. Maybe I have a 2-year-old son who I hope and pray that he will be there to see it. He might be in his 80s at the time. But that is the future, and it's close by. Most of us, God willing, will be here in 2050. So what is farming in that future going to look like? And at this point, I wonder if, Mr. Femi, I wonder if is there a way for people to engage through chat or responding, or will this mostly be a one-way thing?
Yeah, people can actually respond through chat from LinkedIn and also from YouTube. And we can
I
also
see.
pop in, we can also pop in their comments on the screen.
I see. Okay. So, but should I expect responses, or I should just kind of go ahead and if something comes in, I can incorporate it. Is that what I should do?
Yes.
All right.
I think the latter is.
All right, that sounds good. Okay, so I was hoping that it might be more interactive, but I think it's fine. We can go ahead. So this is an image that captures what some people have imagined to be the future. So I'm just going to switch back. So this is an interesting image here that shows what one imagination of the future of farming, right? Where you have this autonomous systems all around. You have autonomous vehicles that are in the air, like drones. You have ones on the ground with different form factors doing different things. The other thing that you see here is a mix of livestock farming plus crop farming plus different things, open grazing, and there's this interesting regenerative farming approach that is really idyllic, right? It's interesting to see how we can potentially, one instance of the future of farming could be that we leverage technology to enable sustainable practices on farms, increasing yield, but also increasing biodiversity and sustainability in how we grow our food. So this is one image. There are other images that you can think of, but I think this was one that was particularly aspirational for me. Okay, one thing that you don't see in this image though is people. You don't see people very much, and that's because people, let's say robots or autonomous systems, are sort of taking the role that people currently take. All right, so this is one version of the future. This is not, I'm not a prophet. Whoever generated this image is not a prophet, so it might not be the actual future, but I think it's an interesting feature to consider. The goal for this talk for me is twofold. I would like to expose all of you who are listening on LinkedIn or on YouTube, expose you to the exciting trends in agricultural robotics, and then also sort of motivate you to explore this space, right? I'm assuming that a lot of people who are listening might be from the African continent or maybe Nigeria in particular or anywhere else. Wherever you may be, exposing you to the trends and motivating you to act in a certain way aligned with your interests. All right, and this is the roadmap for the talk. We have lost a little bit of time, so I might move quickly on some things. But in general, I want to go over, as an academic, I was particularly interested in making sure I set the proper foundations. So the foundation is, what does our food system look like? And then talking about why robotization of agriculture is becoming a significant trend. What is driving that? And then I'll talk about some of the fundamental robotics technologies that are existing. And then once I do that, I can tie that back to agriculture application domains that are currently being explored globally. And then finally, my hope for number 6 was to have an open discussion about opportunities that people might be seeing for agricultural robotics, specifically in Africa. I don't know whether this platform will make that more or less easy to do, but we'll see. All right, so we'll start with the first one, an overview of our food systems. And this is a really good image that kind of captures that. Hopefully this is not new to most people, but there are a couple of stages in our food system value chain. All right, so there's production. This could be livestock, this could be fishing, this could be crops. And that is where food is generated. This is grown, this is harvested, this is caught, and then it is processed in some way. Different kinds of foods get processed in different kind of ways. After processing, it is, maybe potentially, packaged into some form, and then it goes into distribution. Now, through distribution, it gets sold in a retail store, for example, that can get into your home. Hopefully, most of you are eating today, so this is probably how the food came to you. Or you could go to a restaurant and be prepared in a different approach. All right, so that's all interesting. I would like to make this more concrete with a personal example. Okay, an example of poundo yam and egusi soup, which is my favorite food personally. And in particular, I'm using the Ayola poundo yam example. All right. And so how, we eat this food. I eat this food fairly regularly. Maybe some of you might be familiar with this kind of dish. How does this food get to our table? Okay, so I can take this initial map and map it to this concrete example, food production, right? So we grow yam, right? We grow yam. There's an example of yam farm, and we harvest the yam, okay, and then this yam is harvested, is aggregated by different agricultural aggregators. This food is processed. In particular, for the Ayola poundo yam, it needs to be processed. So it is processed. There are multiple stages for processing, and then it is put through a distribution system. So I'm in the US, so I buy this from a store that imported this from Nigeria in particular. And then we buy it, take it home, and then we do some preparation of it. We make it, and then we consume it in the way that it is, right? So hopefully this is not new to most of us, but I think it's important to kind of keep in mind that this is the path from the farm to the table. And there are different ways that technology can impact that process. But in particular, I want us to focus on food production in particular. And how technology, robotics, automation, AI can impact food production in particular, okay? All right, so that kind of moves us to the second part. I want us to focus on food production, and maybe in some other avenues, you can consider the other stages of the value chain of food system, but we'll focus on food production for this talk. And so, open question: if there was some kind of interaction, I would ask, what are some of the stages for food production? What people think, So, and in particular, maybe crop production. So we saw that there's livestock, there's fisheries, there's other approaches, but in particular, crop production. Right. So, what are some of the stages for food production? All right, so I'll move along and kind of present what those are, assuming that maybe interaction might be limited because of the platform we're using. But usually when I teach in my school, I try to make sure that I'm getting students or people listening to engage, and that helps with the learning process. And so people are less passive but more active in their engagement. But I'll move on. So there's this interesting cycle of how we produce our food. Right, and with interaction with the land, right? So when we're doing cropping, we're doing farming, we have this interaction with the land that we go through cycles of engagement with the land to produce food. The first thing we usually do would be to prepare the soil, the land, to prepare the soil to take in our inputs to be able to grow food. All right, and then so after the soil is prepared, we sow seeds, and we apply other agricultural inputs like fertilizers and manure and other forms of resources that the soil needs to be able to be enriched with nutrients to support growth of our crop. And then we, additionally irrigation, and then we weed, and then we harvest. I mean, then, there's time in between, and some things are take, multiple times. For example, between irrigation and weeding, we need to go cycles, different times, different stages of crop growth. I mean, ultimately, we will harvest our crop, okay? And then we go back again, right? So depending on the type of crop, you would do that on an ongoing cycle, right? At different times, different cycle lengths and whatnot. But this is a general gist. There might be a few things missing or things that need to be turned around. But in general, this is like a standard approach for thinking about the cycle of food production. We prepare the soil, we sow our seeds, we apply fertilizers and water the ground to make sure it's in the right conditions to grow. And then we remove weeds that could compete with our actual crop for nutrients. And then once they are grown and they're harvestable conditions, then we harvest, and then we rinse and repeat. Okay, so this is a general thing. And now, that gives us a background of food production, and I'm going to circle back to that background once we start talking about application domains and how robotics can serve in all of those different stages of food production. But for now, I want to sort of highlight why are we thinking about automating or applying robotics to that food production cycle? It's an important question. Why is that the case? Again, I was hoping that we could get some back and forth, but I'll move on, and hopefully, we can achieve that a bit more toward the end. But there are a few reasons I would like to highlight for us. The first reason is global labor shortages. Okay, and this is a particular concern with countries in the West. The West, I mean, in the U.S. and in Europe. And this graph you can see from the World Bank. The global share of workers in agriculture has continued to decline for decades, right? And what that means is that you have fewer and fewer people on the farms to perform the different farming activities that are required, right? So, for example, people to handle driving of tractors, people to handle seeding and planting, people to handle weeding, people to handle harvesting, especially as well, and everything within the farming, the crop production cycle. We need people, and the pot of people that can do that is reducing continuously. Now, this is not necessarily the case in Africa and other developing countries, even though we see there's urbanization that is causing more people to sort of not consider farming as a career, but a large population of people, for example, in sub-Saharan Africa, are still in agriculture as a business. But globally, there's farming shortages and there's labor shortages for agriculture. The second reason why people are looking to robotics and automation in agriculture is to try to apply these technologies to mitigate the adverse impact of climate change. Okay, these impacts include more frequent adverse weather conditions. So it might be droughts, where there's lack of sufficient water, or there is flooding, which is too much water, that unsettles the balance of conditions that you need for your crops to thrive. Okay, and in this image I'm showing here, you can see that when you look at the regions of the world that are most impacted by climate change effects, you can see it's those just around sub-Saharan Africa, within the equator line, and not just in Africa, but also across the world. Okay, and so it's something that, especially in Africa, we should be concerned about. How can we become more resilient to the adverse effect of climate change in our farming and our agricultural practices? In particular, in Africa, sub-Saharan Africa, there are concerns about food insecurity. So we need to be particularly careful and thoughtful about how we sort of mitigate this impact. All right, and speaking about food insecurity, the third reason that's driving robotization of agriculture is the need for increased yield and productivity, right? So crop yield and productivity of our land is important, particularly because of our increase in global population. All right, so we can see in this image here, we see trends of global population. In the developed world, that number is the trends are mostly flat, but in the developing world, particularly in Asia, Sub-Saharan Africa, we can see that trend really going up. And with more people, there's more food demand, right? And so more food demand means we need to increase the yield, and also we need to increase the productivity of our cultivated land, right? And so how do we achieve that? And to now be more in particular for Africa, food production in Africa in 2050, we say we're talking about how farming will look like in the future, 2050, 2100. With this image, you can see that the current trend is showing that we need the amount of yield that we need from our land in Africa to feed Africa needs to be about close to 3 times as much as what it is today, right? And so there is that deficit, there's this gap that exists and that seems to continue to grow. And what we need to do is to find a way to bridge that gap, right? And one approach, there are many approaches to achieving this. It's a multifaceted problem that requires multifaceted solutions. But one of those solutions is perhaps applying robotics and automation to increase yield and productivity of our cultivated land. Okay, so these are the 3 primary things that are on my mind and in kind of the general discourse. I'd have been curious to hear what other people have in mind about some of the things that are driving applications of robotics in agriculture, but maybe that might come up as we have more people engaging through the chat, perhaps. I had a comment about how do we respond. In particular, we can think about, can we develop digital skills and competencies and connect those things to finding opportunities that align with our interests, and specifically in the area of technology for agriculture. And I just want to give a shout out to Precision Field Academy for this opportunity to train people to develop those digital skills and hopefully link them with opportunities that allows them to be change makers. That we all need to contribute to addressing this food gap, this food deficit that is growing and continues to grow, and we need to all contribute, lock in arms to address the challenges. Okay, so we sort of covered an overview of our food system. Hopefully that was interesting to you. And then we sort of outlined some of the driving factors for automation and robotics in agriculture. And then now I want to just introduce us to some of the fundamental robotics technologies. I'm going to say that this particular section of my talk will focus on robotics in particular, a little bit of AI, but particularly robotics and AI, maybe a little less of automation more broadly. And then all those things are interconnected in some ways, but strictly speaking, we'll focus more on robotics. Okay, so I'm going to go over 3 fundamental robotic technologies. These are not all the fundamental robotic concepts or technologies that are applied in developing systems for agriculture. But I just want to pick out these three. These are three of the most relevant, I would say, but there might be others as well. All right, so there's visual perception. There is auto guidance or autonomous guidance systems, and then there is robotic manipulation. So the three fundamental technologies or concepts that I would like to motivate us with today. All right, so the first is on visual perception. It's also called computer vision. People can also call it computer vision. Essentially, how do you get a computer or a machine to be able to not only acquire visual information about the world, but be able to process this information in a way that provides it with reasoning about the world. Okay, so that's the perception part. So God has made animals and humans to have these naturally. We have eyeballs, we have brains. Our eyes capture visual information, our brains process that information to tell us, to give us inference about what we're seeing. And then as engineers, we try to recreate this visual faculty with machines. So machines can be able to process information. It's very important, right? Farming is a very visual thing. You need to see things to be able to act upon it. And so that's why visual perception is very important. Okay, so I have a few videos just showing you different applications of how visual perception is applied. I'm going to review. And so just give you some ideas. On the left, the video on the left is essentially performing crop yield estimation, right? So you're using camera that's on a drone to fly through a pumpkin farm, and it's able to distinguish between the white pumpkins that are maybe not yet ripe and the orange ones that are ripe, and can count to get a sense of what the harvest could look like, right? What is the yield? And then on this side, this is showing a video of again, aerial images from a drone over a field, and using computer vision, we can detect different crops, distinguish crops from weeds, and collect the types of weeds, classified what types of crops, what types of weeds, and that allows you to have information about how you can go about doing your weeding, right? And so these are all visual information that are being processed by some system to enable us to make decisions like a human being would about our farming practice. Okay, so how does this happen? Is two stages. The first stage is in image acquisition, right? So essentially just how do we enable computers to collect visual information? Okay, so this is usually done through like image formation, digital image formation, lights, rays that go from an object goes through a process, including focus using a lens, impressing the information on some kind of light sensing system that then collects that from the light rays, collects information light rays, and digitizes that. And ultimately, so it's going from an object into light into a 2D image on the back end of your camera. This could be a film-based camera, or it could also be a digital camera like we usually use nowadays. And that's what you can see in this pipeline. All right, and so it's primarily, it's very similar to how our visual faculty works as human beings as well. Light goes in through our eyes. We have a lens, we have a retina. The light falls on the back of our eye, where we actually have special neurons that have the capacity to interpret light rays. And so a very similar structure. But anyways, the point is that from a digital perspective, we can generate digital images through light, through special lenses and sensors. Okay, now once we have an image that's like in here, so an image maybe from a camera or from whatnot, we need to process that image. All right, so there are different computer vision pipelines. There's a traditional pipeline that uses maybe more traditional image processing tools and techniques. And then we can then set different kinds of classifiers to define what we want to do. So we collect our image, we process it somehow, maybe to extract particular information from it, and then we can use machine learning to determine maybe whether this is a weed or whether this is a crop, for example. And then more recently, with the advent of deep learning in the past maybe 1 or 2 decades, the deep learning pipeline has become a lot more prominent. And this in a general gist, deep learning networks allows a machine to learn almost everything that you might have needed to do previously through the traditional pipeline. It can learn the features that you're looking for in an image. It can learn how to distinguish that at different levels. And then it can also learn how to classify, to tell, oh, this is a weed, or this is a crop, or this is a goat, or this is a cow, or how to segment different parts of a particular image. Okay, and so these are the 2 different pipelines. I have an example here of a traditional pipeline that is being used for, I think this is for weed detection again. And so you can see input image, you can play around with the color spaces. Color spaces are just different ways of transforming an image in your color spectra. And then we can extract different features of how the images play out in your color spaces. And then we can use different algorithms to sort of remove background and different things to distinguish what might be a crop and what might be a weed just based on the color features in this particular case. Okay. So visual perception is a very important part, fundamental concept and technology that we use in robotics to enable a robot or any system in particular to be able to collect information and process that. One thing I wanted to add that is beyond the visual spectrum is, maybe not beyond, but expanding the visual spectrum. Usually when we think about the cameras, we think of the traditional RGB, or the 3 color space, the 3 bands, but there are other approaches of collecting more data from our visible world through multispectral and hyperspectral imaging, right? And that way we are collecting multiple samples of wavelengths from our visual spectrum that we are perceiving. And that way we can actually study and understand more granular things about the world, particularly maybe about our plant or about our crop or about our fruit. We can tell more important things beyond just the RGB colors, right? As human beings, we use a lot, we apply a lot from our RGB, but then going beyond RGB to higher spectrums, or like higher, let's say higher resolution of our spectra, we can actually get much more information. All right, so that's for visual perception. The second fundamental technology is on auto-guided systems. Okay, so I have this video which are showing. I think I'll just let this play. I don't know if the audio is coming through well.
It was really exciting the first time I got to take the autonomous tractor to the field, swipe my phone, watch the tractor start.
Yeah, it's a little bit faint, but we can hear.
Okay. All right. Yeah, I mean okay, thank you. So this is showing a John Deere tractor. It's an autonomous tractor. I think John Deere is a popular tractor manufacturer globally, probably the largest in the world. And so within the last 5-10 years, it's really been investing a lot in autonomous tractors, right, and enabling a tractor to not need to be driven by a farmer or a driver, that enables it to actually drive autonomously, like you can see here, performing different farming tasks on the land autonomously. Okay, so the question is, how is enabled? What kind of fundamental concepts enable us to have a tractor that does not need to be driven by farmer? Okay, and so this is an interesting block diagram. It sort of shows the main components. Fundamentally, at the core, there is control, right? So you're interpreting sensing information and determining how to steer and how to move. The control system for an autonomous vehicle is very similar to the control system of a driver, right? And so the driver is using its sensors to know where am I within the farm, and where do I want to go to, and communicating with other people or other components of your farming practice, and then steering or using the different pedals on the tractor to control the vehicle to move. Well, but that's very similar to how a robot would do it, right? So it would process sensor information, GPS or other sensors, and then calculate where it should go, plan a path, and then ultimately it will send steering and speed commands to the engine of the vehicle. Now, a lot of this has been existing for many years, but what really unlocked the capability of auto guidance in farming is GPS. How GPS became more mature, more accessible. That really enables you to have precise positioning. I know that I think there have been other talks about satellite navigation systems in this incubation program. So I'll not delve too much on this, but in particular, using the GPS, which is Global Positioning System, as the US version, more generally it's called Global Navigation Satellite Systems. That enables you to get significant accuracy of your geolocation anywhere on the Earth's surface. Okay, and when we include other measures of correction of our general GPS information, we can actually get better levels of accuracy. And so that video I was showing you about the John Deere tractor, with the right type of GPS system, they can be getting centimeter level accuracy of where the tractor is every moment in time. And if you know where you are and you have a mapping of where you want to be, then it's fairly easy for you to then say, okay, should I turn left, should I turn right, in order to go from where I am to where I want to be. Okay, so that's fundamentally how auto guidance is enabled. But there's also scenarios where you do not have GPS. That's usually not necessarily in the case specifically of the general applications in agriculture, because agriculture is usually outdoors, and outdoors you usually have access to GPS. But there might be scenarios where you are a smaller type of robot operating under canopies, crop canopies. In that case, you might have intermittent access to GPS signals. And in those scenarios, how do you then provide your localization information? And so there are approaches to use other sensors. In particular, this example I'm showing you in the video is using camera information. All right, so, and it's following the crop row. So you can follow crop rows using camera information to stay on the path without needing your localization information from GPS. So that's an interesting application that enables just more robust auto guidance system for farming, where you're no longer dependent on very accurate GPS information all the time. In cases where maybe the GPS information drops, okay, you can use other sensors like a camera to follow crop row. And then also all of this applies to drones and UAVs. So that's just something I want to mention. Drones also have GPS connectivity to enable them to have precise localization. Usually GPS is used, drones, UAVs use GPS as their primary source of localization. And so that same thing. And then also you can plan a path using your drone, relying on GPS information. And then your drone, if it has the right control capabilities, can follow that path by steering left, right, up, and down. Similarly to the way that a tractor on the ground would do it. And so That's sort of summarizing. To summarize, the auto-guided system is a very important part of how we enable robot systems to operate in the farm. And the third one is robotic manipulation. Okay, so manipulation is how can you interact with crops in this particular case. A lot of times it's in the space of touching, holding, pulling, pushing, different kind of things. So I'll show some videos just to motivate. So this is a harvesting scenario where you have this robot. It's also mixing with visual perception to know where the fruit is here, in this case, the bunch of grapes. But then it has this arm, right? This robotic arm that can reach and actually harvest the grape, which is really interesting. The other example is a different scenario. Let's watch the video.
Voor ons interessant vanwege de minimale vertraging en de gegarandeerde bandbreedte. Dus dat we altijd de robot vanaf afstand kunnen besturen en vanaf afstand kunnen instrueren en bijtrainen.
And so this one in particular is using a robot arm for weeding, right? So it has that robot arm that can actually do precise weeding, and I will show a bit more about that later on. But so in general, manipulation is using robot arms to be able to manipulate your environment, like the two examples I showed with harvesting or with weeding. There are generally two types, the two main types. There are a few other types, they're hybrids or mixtures, but there are two main types of robot manipulators. There's a serial link, that is where all the different links are serially connected in a kinematic chain. And then there's a parallel link where they are not connected end to end, but they are sort of parallel to each other. Okay, so that's like the general gist. And usually manipulators have something that we call an end effector, which I'll talk about also. So these are the two main types of manipulators. The first type is the serial link, and there are different configurations based on different joint types. All right, so the human arm, for example, has different kinds of joints. But for robots, we have, rotational joints. We have, let's say, prismatic joints or joints that go in and out. And then how we configure, how we combine those different joints allow us to enable different kinds of motions. Okay, but the most common is what I'm showing here on the screen for the robot arm that has primarily rotational joints. And so this robot has six joints. So there's one here, 2, 3, 4, 5, and then there's 6 here and at the top of it. And that allows it to be able to actually move with a lot of flexibility, changing both its position and its orientation in space, which is really really versatile for different applications that we can use. Okay, for parallel link manipulators, usually you have the different links that are connecting both from the base to the end effector, like you can see here. All right, so these are the different links, and they are all connecting from the base to the end effector. This is the base, this is the end effector. Similar thing. They're very common in manufacturing because they have particular unique characteristics. The unique characteristics are that they can be very fast, they're more sturdy, more stable, but even though they have a lower payload. This is an example of how it would work, right? So you can see you can put an end effector at the tip of the robot, the parallel link arm, and then it can pick and place things. So this is particularly an interesting application of manipulation that we see as well in agriculture. Okay, and then the last part of manipulation is with the end effectors, okay, or the gripper. You can call it end effector, you can call it gripper. It's usually the thing at the end of your robotic manipulator. Okay, either it's the robot arm or the parallel link, the thing at the end, the thing that actually does the interaction. Okay, so there are different forms, there are different types. This just shows a taxonomy of different types. The active grippers, the passive grippers, the grippers that have multiple fingers like a human hand, There are ones that use vacuum. They're vacuum operated, or they're electromagnetic operated. There's some that have, they're made with soft material. There's some that are more rigid. So there are different applications, and usually people actually design different grippers for their different applications. Okay, so for some applications, you might need to have more soft material to interact with the crop. Like, for example, here they're using some mixture of suction plus more soft material. In other cases, you might be able to get away with more rigid fingertips, like these ones here that are in the context of agriculture that can be used for weeding. The example that I showed you earlier was for weeding using this kind of 2-finger pinch grip kind of setup. Okay, so let me see if I just go back. So in general, these are the different structures for manipulation. You have both series and parallel links, and then you have end effectors at the end. Okay, so I was going to ask, ask people if they could tell what type of manipulator that we have in these 2 videos I showed you earlier. I might skip that, but just to show you, think about what it might be. This is a series. This is series link manipulator arm, right? And then on the end there, that is the end effector. All right, this is the end effector part that is at the end of your manipulator arm. That's an example. And in the other case, it is, let me see if I can show.
Dus dat we altijd de robot vanaf afstand
see if I can get an image. Yeah, so if you see this is similar to the parallel link case, right? And then you have just the 2-finger gripper, like I showed you. All right, so you can see different applications have different manipulator types and also different end effector types. All right. Okay, so that covers. We've covered a lot of things. We have looked at our food system. We've looked about why people are approaching, or what are the trends that are driving application of robotics in agriculture. We looked at some of the fundamental technologies that underlie agricultural robotics. So we looked at perception, visual perception. We looked at auto guidance systems for navigation of autonomous systems. And then we also looked at robotic manipulation. Now, in this section, I just want to motivate us with some different application domains. I might be a little faster here because I know we're a little bit low on time at this point. But just want to show us different examples of application domains. So it's mostly just me showing you videos that can get you thinking about what's possible. Okay, how I want to do this is to go through each of the different food production stages that I showed you earlier and say, okay, how is robotics applied for each of them, right? How is robotics applied for preparing the soil? How is robotics applied for sowing? How is robotics applied for irrigation, for harvesting, and whatnot? And then I can kind of get us thinking about more broadly what the breadth of robotics applications in farming or food production in particular. All right, so we'll start with preparation of soil. This generally includes plowing or tillage. So this is an example of a different type of John Deere autonomous truck. This is an electric truck, so it's fully electric, no diesel. And you can see in this case, it is pulling this farming implement that is tilling the ground. Okay, so this is a very common application. You know that in farming, land mass can be huge. In the US here, you might have a piece of land that is 5,000 acres, of land that you can't even. It might take you hours to drive around. And so you can use an autonomous vehicle that can do your tillage day and night, and allows you to do things more quickly, minimize the impact on labor, especially when there's labor shortages. Okay, the other application is in seeding or sowing, right? So you can think about digging also think about direct seeding as well. This example of a robot manipulator arm, you can see that is actually doing seeding in a nursery or like a greenhouse scenario where it is then transplanted to the field afterward. It's an interesting video. I will see if I can, let me just play it again so we can see the robot.
Amazon rainforest, known as Yumi and created by ABB Robotics. It can sow about 600 seeds in a morning's work, the equivalent of 2 football fields in a day.
And the other one here, maybe I can make this a little larger. This other one is a digging robot that it's used to prepare for for seeding or maybe transplanting in this case. The robot just moves around the field and digs holes in it with the right depth into the ground, and then afterwards either through an automated system or otherwise people can come and now either do transplanting or maybe direct seeding. I'm not sure what application will be used there, but I think both will be fine. Okay, and then the other one, which is really an exciting application of robotics for seeding, is using a drone to do seeding, right? So they actually have this drone that can, it's a long video. Don't have time to let me see if I can pull up that part again. Let me see if I can move. And so we use this drone to fly around, and it has some seed application at the bottom end that shoots seeds into the ground from the air, right? It's a really interesting application. Again, you can see how it is weaving visual perception or autonomous guidance system and robotic manipulation. Most of the applications that we see would be applying these fundamental concepts in different ways. All right, and then the other application would be like chemical application, fertilizer or pesticides and whatnot, herbicides, different things. It's very common to use drones. In this case, I think this is the bread and butter of Mr. Femi's company, as integrated aerial precision. So using large drones to apply different type of farm chemicals for farm for agriculture. So that's including fertilizer or pesticides or even irrigation as well. Right, and so this is a very common application that we can see of using drones. I'm sorry, using robotics, in particular drones in this case, for crop chemical application. Again, similarly, right? So irrigation, I just wanted to also capture irrigation as well. There are different approaches. Instead of using a drone in this case, you can also use a ground robot that has similar sprinkler system, sprinkler or sprayer system that can move through your farm and apply your inputs into the farm in different ways. So this is a different approach as opposed to using something aerial that is not impacting the ground. This one will actually be a ground robot that is also autonomously driven, right? So it's driving autonomously, no one is controlling it, and it is able to do variable rate control, determining what parts need more watering, what part needs less watering, things like that are enabled through robotic technology. And then weeding is an important part. There are different approaches to achieving weeding through mechanical weeding approaches or chemical. In this case, I'm actually showing this company called Carbon in the US. And they don't use mechanical or electrical, they actually, or chemical, they use laser. They actually use laser to kill weeds. So of course they need to be able to tell which is a weed and which is not a weed, and then they can apply specific, very high level of precision of positioning of the weed, that's so shoot a laser at the weed. So that's a very interesting application. This one I think I already showed us earlier. That is using a robotic manipulator to pick weeds from the ground.
Minimale vertraging en gegarandeerde bandbreedte. Dus dat we altijd de robot vanaf afstand kunnen besturen en vanaf afstand kunnen instrueren en bijtrainen.
Deze robot is ontwikkeld vanuit de behoefte dat we niet alleen
Gebruik kunnen maken van diezelfde.
All right, and then I think the last one here is harvesting. Harvesting is a very big part of agriculture, as you can imagine. That is where we pull out the things that we care the most about, the fruit of the crop. And so again, here a lot of automation has been applied. This is one of my favorite concepts. That is using drones to do fruit tree picking. So this is like picking apples from the tree directly using drones. The drones have this manipulator that can go and using suction can actually pull out the fruit from the tree. And then this is another example of not using a drone, but using a ground robot. And this is particularly in the application of harvesting strawberries. Strawberries are particularly hard to harvest. They're very small, they're very delicate. Any kind of pressure on the actual fruit can damage it, and that limits its commercial value. And so people have explored how to use this really intricate robotic system to identify where the stem of the strawberry fruit is, and be able to go and hold it by the stem, cut it by the stem, and delicately place it in the basket. All right, so that sort of brings me to the end at most of what I wanted to share with us, and I think we're maybe doing okay on time, so that's good. The last thing actually was supposed to be an open discussion. I wasn't sure what the format for this talk would be, but I think we can just mix that up into the Q&A if people have questions at this point. But I wanted us to have an open discussion about, what opportunities are you excited about? And I've shown you different applications. Again, my goal was not to teach you all about robotics and agriculture. That's not possible in a 1 hour lecture or talk. But I want to just kind of give us general ideas of the breadth. I wanted to expose us to some of the application domains. I wanted to motivate us to think about what other people are doing and how maybe that might connect to things that we might be interested in. And so now I'm actually curious to hear, if at all possible, whoever is in the audience, what opportunities are you excited about? And what things have you seen that make connections for why in Africa or wherever you are, we should be considering applying agriculture and robotics to agriculture?
Yeah, Dr. Kenny, I don't know if you can see the screen.
Okay, now I can. I shifted my, yes, I can see the screen.
Okay, so we have a comment from Joseph Adeyemi. If you can read that. It says robotics has more value to offer than we can imagine. Robots and automated system can save time, cost, and perform dirty work, or repetitive tasks.
Right. That's exactly right about how I think in particular, and what I see in the research that I do in agricultural robotics in the US, so this is in the West, so it's a little bit different from maybe other regions of the world, but particularly in the West, where there's significant labor shortage in farming, people struggle to find farmers to do the difficult work of, for example, weeding. Weeding can be very challenging, especially for specialty crops. So specialty crops could be like vegetables and the other types. It's very challenging to weed. A lot of times people resort to hand weeding. There are a couple of mechanized approaches for weeding, but they're not perfect. And so these are dirty, difficult, challenging tasks, especially in the summer when it is really hot outside, hot and humid. To have people bent down, weeding can be very challenging, or thinning as opposed to weeding as well. And so if there are areas that robotics can enable to take up some of the laborious tasks required by farmers, open them up to other opportunities or higher value tasks that people can take instead of doing this lower value tasks. It's definitely something that's appealing for robotics. So yeah, thank you, Joseph, for your comment.
Yeah, thank you so much for that. I'm trying to scan through the comment section. Okay, I think we have a question here. So, same from Joseph Adeyemi is asking, how do robotics, automation, and AI contribute to reducing environmental impact of farming practices, such as targeted pesticide application and soil health monitoring?
Yeah, so that's a great question. But you kind of answered the question yourself with those two examples, right? So targeted pesticide application and soil health monitoring. Maybe I can elaborate a little bit about those two particular areas of robotic application. And so the first is with targeted pesticide application. And in particular, it's fundamentally saying that there are, in your field, you have a large field, maybe 100 acres, maybe 1,000 acres. You have hundreds of, you have tons of produce on your field. One way to think about your field is that it's a homogeneous space, right? Everything is the same. But that's not actually the case. Some patches of your field might require more or less inputs as other parts, right? Some parts might be dry and hence require more irrigation. Some parts might, because of the soil context, might require more fertilizer. Some parts might require more this or that, right? And so if we can unlock that information at a large scale, so that we can then be more strategic in how we apply our farming inputs, we can not only save costly chemicals that are required for farming, okay, but then also, so you're saving instead of spraying 100 gallons, you're spraying maybe 50 because you're only spraying in the areas that require that amount of input. But then also in particular with pesticides and herbicides that actually have been shown to have adverse effects on the soil or on through runoff on other water bodies, we can reduce that. We can have more target, like you said, more targeted, or maybe a spot spraying or specific selective spraying of our pesticides or herbicides in the areas that actually need it. So in particular for weeding, for example, instead of spraying the entire field, can we just do particular targeted spot spraying on the weed, reducing the quantity of herbicide we need to apply, but also reducing the impact on the environment, And then secondly, so soil health monitoring, yes, we can tell using, so this is more on the visual perception side. We can tell how the soil is doing through imaging or through specialized sensors. We can also tell how plants are doing or crops are doing through imaging. We can do crop phenotyping to understand the species and how that develops. So there are many ways that we can tie in these technologies to use them as enabling factors for being more efficient in how we perform our farming, reducing the burden of farm inputs, like water, like energy, like chemicals, those things that are needed for farming, but are constrained because of environmental considerations. But even an excess of them could also lead to negative environmental impacts. So these are different ways, and we could talk on and on about different other ways of using these technologies to reduce environmental impact. But those are some of the things, and thanks for sharing some of those examples.
Awesome. Yeah. I mean, you have actually shared quite a number of things today, and myself, I'm actually thrilled. And you actually gave some bit of clarity and context to even things that we have around us already, how we are actually using them. And you mentioned about visual perception, you mentioned about robotic manipulation. You also mentioned one other, keep my mind now.
Oh, the auto guidance system.
Yeah, the auto guidance system,
Mhm.
particularly. You actually shared that. And the auto guidance system, particularly, can it actually work without a GNSS? Are there auto guidance systems that actually work without GNSS? And what, for example, you will not be able to have a good signal of GNSS in indoor application, or what do you leverage in that? Yeah, I'd like to. I think we still have some other questions too.
Yeah, so I think that question, that's a really good question. My understanding, the large majority of ways that we do localization on the farm would be through GNSS or GPS technology, because it's the most I'd say robust in terms of access. But however, like you mentioned, and like we talked about earlier, there might be scenarios in which you do not have access to reliable GNSS signal. And so that becomes a challenge. There are different ways to achieve localization, which is essentially what your GNSS is providing or positioning without GNSS. But the one I showed in my, maybe I should go back there. The one I showed in this presentation was particularly, let me go back there. Right. Yeah, it was particularly using, so instead of using GNSS, using visual information. Okay, so using visual information, and particularly using a camera and information you can get from a camera. And so this is an interesting application. The different ways you can use a camera to get a sense of your localization. This is using features in your farm. And this is particularly just for crop row, like crop row following. So this is a limited application. But other applications could be, other technologies could be using what is called visual odometry. That is essentially using your camera and the feed from your camera to get a sense of how you are moving in space, right? So you can use information from your camera to tell whether you're moving left or right, and some sense of how fast you're moving. And that could, if you know your origin location, you can use that to sort of estimate where you have been since your known location. But those techniques are, they're prone to drift and errors and things like that. So usually people would try to use them as stopgap for when you lose GPS or GNSS signal, but usually not entirely. I don't know if there's scenarios where people on a farm would completely disregard GPS entirely and use other methods, because GPS is really reliable on the farm in most cases.
No field.
Yeah.
Right. Yeah. Because there are some agricultural applications that are actually not on the open field, where you actually have that direct satellite connection, as compared to indoor environment, so like protected area cultivation, maybe inside a warehouse or something indoor enclosed, that we need a robot to actually get inside and just work. Yeah.
Yes. Yeah, maybe for example in a greenhouse, or in I think greenhouse is probably the most common example of sort of indoor scenarios, or in places that are more enclosed. Yeah, that's true. That's a good one. I think that when you are indoors, it presupposes that you're in more controlled environment. Okay, so indoor environment is a bit more controlled, and once you're in a more controlled environment, there are many things you can do to allow you to determine where you are in that context. And so people could still use some. I think usually people use some visual or some other ways. They're indoor approaches using auto-band positioning, wireless type of communication to provide position information. People would also use other like visual fiducial markers around the space that cameras can pick up to tell where they are. So there are different applications that you can use if you're in a controlled indoor environment that might be less less accessible if you're outdoors.
Okay, yeah. So I have some comments here and question. Michael Alipo is saying, I am excited about the opportunities robotics hold for weeding our farms. These days, even in Africa, it is a struggle to get farm labor who come with high costs to weed, especially during the farm season. Yeah, he's just making a comment for that.
Yeah, I agree. I mean, weeding is probably one of, at least in my sense, I'm not a farmer. I've never really been a farmer. I'm coming to farming with my perspectives as an engineer. So I try to come to farming with a lot of humility because I haven't been a farmer personally. But from my discussions with farmers, which I do a fair bit about, I do a fair bit of interaction with farmers to understand the context, to inform what I design as an engineer. Weeding usually comes up as the most challenging task, right? If harvesting is also difficult, but it's more exciting. You know, this is the produce, this is the outcome of your labor. But weeding is kind of like, how do I remove this pesky, annoying things that are kind of trying to impact my my crop? And so it is difficult, it's challenging. There might be different scenarios in which you will be weeding. And so yes, I think that weeding is, from my assessment of the various applications of robotics in farming that have gotten the most amount of reception and the most amount of let's say funding from companies receiving funding. There's a lot of it for area like drones, for different spraying applications, but for like ground robots, it's specifically in the area of weeding and harvesting, because those are the two most laborious tasks, and those are the two tasks that have the most impact on bottom line. How you yield, so preserving yield. So yes, I'm not very familiar with weeding applications or robotic applications for weeding in an African context. There's maybe one or two companies that I've interacted with that are trying to develop those kind of technologies. But these are, there are a lot of global companies that are doing this, and I imagine that some of those technologies can trickle down even to Africa so that it can benefit farmers there too.
Yeah, and that's actually some of the things that we are doing with our drones, like you mentioned. We just hope that we can be able to have more of these solutions, and our students at the Shumfield Academy would be leading in this, for us not just only to be observers or consumers of technology, but to be players, innovators and inventors, this technology, robots that fit into our context. Our context is actually different from what we have in the West, although there are similarities, but it's actually better for us to actually create something that is fitted for our climate, for our weather, for our system of agricultural system, compared to adaptive mechanism or improvisation as it is. So, and that is why we are actually having class like this for leaders like you to enlighten us, to open our eyes, and also to inspire. I believe that if we actually have such amount of people like Dr. Kene, we believe that Africa is actually is actually on the track to get to that point where we can be able to have many of the solutions. Okay, I will move to the next, and I think this is very, very critical. From Adejoko Tose, it's asking, say most of the precision and robotic farming are crop-based and less of livestock, apart from digital fencing, artificial insemination. adhere more to robotics and precision in livestock production? I would like to hear from you. I think I also have a comment for you.
Yeah, that's a good question. That's a very good question. I really can't say I know very much about livestock production. And so I'll probably defer to you, Mr. Femi, about this. The few comments I can provide is yes, I have seen a few applications that may be beyond digital fencing and insemination. For example, people have used different computer vision techniques to monitor livestock, maybe like chicken or like for poultry or for cattle, for example, or for swine, to monitor their movement, monitor their growth using camera information that you can process to count or to study the changes in their in the livestock. And so there's some applications of using camera information to harvest data that might be useful to inform some things. There have been applications I've seen. I haven't studied personally, but I've seen applications of using small robots that can maybe do cleaning of like a poultry farm stead or a piggery as well. So there are different things. I think it's an open area. It's an area that I haven't personally studied very much, and so my focus in this presentation was more on crop production. But I imagine someone else with expertise in that area could also give you a 1-hour lecture about the different available applications.
All right, very good. I think you've actually mentioned majority of the precision and robotic application are actually in crop production, and I think it justifies for it because because crop production is actually the basis. You actually do a lot of crop production at scale, at massive scale. That you might actually have to employ the whole town to actually do some farms, But majority of livestock are actually intensive, and intensive. But this does not say that we do not have application. Even as the country representative for ISPA, that's International Society for Precision Agriculture. Recently, the definition of precision agriculture was actually updated to actually make it inclusive for precision livestock farming, and yeah, so it's the same concept, the concept of understanding the variability between object of interest. Let's now say in your flock, how can you administer the right drug that is not just hot for the head, but particularly for animal with tag A, with a tag B, specifically measuring their body temperature, specifically, not just giving them maybe the same quantity of feed. How can we also monitor individual animals? There is a saying that says what you cannot actually measure, you cannot actually manage. So I think we have a lot of applications like the AirTag that uses IoT. We also have, like Dr. Kenny mentioned, something that can actually do the dirty job, cleaning of the manure, scrapping the manure without actually somebody being on the farm or driving the tractor or driving the small, that can actually help. Something that can actually pour feed for our animals, pour the feed for our animals, considering their weight, considering you can be able to ration and say, oh, this animal here, because I've actually weighed it, I can actually, based on there's what we call body feed to body ratio. You can be able to know this quantity of feed you need to actually give to this animal to actually maintain, and you can be able to ration. Ration to actually get the right yield. You are not feeding it too much, but you are not feeding it also less. That's also precision. You're actually ensuring that so that you can achieve profitability. There are also applications. Yeah, You might be saying crop production. What about ruminant animals that need pasture? You know, a cow would actually need at least 1 acre from what a dairy and a dairy cow, you know, would need, you know, pasture development or cultivation. Of course, you can actually use robotics. All of this that we have actually mentioned. It's very, very critical and important. I also know in poultry, yeah, cleaning, feeding, packing of the eggs, right? Picking of the eggs, packing of the eggs, setting it inside a tray. These are actually robotic applications. And as Dr. has actually explained to us, you know, how all of these things are actually automated. You know, these are actually applications. We can also think about how we can actually use them in these applications or the principles of this application in piggery or in rabbitry, you know, these unique applications but the base that you need to first know, you as an innovator, to understand the principle behind these things, what's the principle of precision agriculture, then you can be able to then think about how maybe a robotic arm, maybe perception, maybe all of these things can come together and be able to help us to solve problems or make life easier for you as a farmer or as a professional, you know, particularly. So yeah, that would be my response to that.
Excellent.
We also have, let's just get these two questions and we have it to close. Okay, there's a question here from Joseph. He's saying, it's amazing to see what robotic machines are doing in the video you share. In Nigeria or Africa, how can one navigate high cost of acquisition being a young farmer with interest in precision agriculture?
That's a good question. I'm not sure I have good answers to that question. That is beyond my area of area of expertise. What I would say is that I think Mr. Femi, you touched a little bit about on this issue. You know, this is thinking about what economic models are available and at play, right? So, for example, you might have a company here in the US where I am would develop some micro tractor or some autonomous tractor that's able to do some things. But their goal is to sell it to companies or farms in the US, you know, and those farms in the US have, you know, maybe some have access to funds, some don't have access to funds. And so I guess my point is, I know there are different markets, and when technology is being created in a different market, on the one hand, it might not really be a good fit for an entirely separate market, but also the funding model might be completely different for an entirely separate market. Right. So that's one thing to note. The second thing to note also is that the question you're asking is actually not a unique question to Nigeria and Africa, considering robotics solutions from globally, from the West, from China, from where else. I do a lot of work with small farms in my city here, because the city where I teach is not a large agricultural production state. So most of the farms are small farms that produce vegetables specifically. And they have the same challenge. They don't have access to some of these awesome gadgets because they're expensive. Okay, so there's issue of scale. That's one issue. Robotic solutions are usually expensive. It's not just the thing that is riding on the farm that's expensive, but it's most of the time it's the software and the engineering time that goes into developing the intelligence of the robot that is expensive. So all of that to say that it's primarily an issue of scale, where it might not make sense for a young farmer to buy some of the latest and greatest technology. But as you scale up, as you maybe do some resource sharing with other farms, the economies of scale begins to make sense, right? An example would be, for example, with actually, I'm not exactly sure how, Mr. Femi, how your company operates. But my sense is that the farmer doesn't own the assets, right? So your company owns the asset, and the farmers can subscribe or invite you to apply some of your technology. So that could be a model for a farmer. You don't need to go and spend what might end up being $20,000 or $30,000 on a robot system to put in your farm. You might want to leverage a precision agriculture engineer who is their business of understanding that technology and building a network of farms that they will circle around providing that as a service. You know, that could be one model. The other model is, for example, what the model of enabling more mechanization using tractors in Africa that, what's the name of that company? Hello Tractor, yes. Hello Tractor does, where you have people who will lease their tractors to different farms to do different things. It's not owned, the assets are not owned by the farmers, the assets are owned by the leaser, and they're able to enable that. It's not an easy question. I think in my mind, a young farmer wherever in the world might not have sufficient financing to buy expensive robotic systems. That does not mean they cannot benefit from expensive robotic system solutions. There could be other models that enable them to not need to own the asset, but still benefit from them, like I described. The other thing I want to say about this is that, and sometimes, depending on who this farmer is, if this farmer is particularly interested in precision agriculture, and this farmer has some opportunities to be here in this academy, you can actually get some training that allows you to start playing around with some of this technology on your own, right? You can start learning about computer vision and visual perception. You can start learning about drone technology. You can start learning about IoT. And even in your small way, you can put some of these technologies together in a way that creates value on your small farm. And that allows you to reap some of the benefits. It's not going to be very easy because developing robust solutions is something that people spend years and years and a lot of development funds on. But by, first of all, potentially making connections with networks like Hello Tractor, like Integrated Aerial Precision Company, like other people that can provide an aggregation of these technologies on a subscription or a service basis, or by tinkering on your own as a deep enthusiast who is learning and building skills, you can actually bring some of this value to bear on your farm.
Yeah, I actually agree. And I would actually come from the perspective of being hopeful. And if we look back, say 24 or 25 years ago, I'm not sure, maybe smartphone has got into Africa by that time, but I know there was actually something we call phone, right? Or mobile phone, GSM. The days of Obasanjo, 2023 or 2003. Yeah, I remember very well. So, but not everybody that actually has an answer, But now today we have super cool stuff and it's actually cheap. So I believe that what you're actually doing now to actually harm yourself with the understanding, with the education, two things would actually, you will be aware, you'll be exposed. Number two, you will be part of those who would be leading when there are actually opportunity, perhaps with the model that Dr. Kene mentioned, service, rentage and all that. But for us, we also believe that we are now in the age of decentralization, where tractors are getting smaller. You don't even need to. I also believe that Africa might not need the big tractors like the 350 horsepower and all that. We might not need that. What about the small tractors, small robots like this that can actually help me to plow my land and, electric or just small, portable? And that is what drone technology, I perceive for drone technology, that every farmer in Africa would soon, when the regulation gets eased, when there are more competition, that would reduce the price down, making it available. I believe that this thing will be decentralized. And it is, I do believe also that through education like this, raising awareness and putting up the hunger of people, exposing you, we are going to have more demand, which is going to cause more competition, in the face of a conducive environment for manufacturers. And you yourself, you can also create solutions for yourself. This is why we're talking about this. You can be able to put one or two things together. In our academy already, we have guys who are actually doing stuff, who are actually having soil sensors, to actually determine the moisture. These things are there. It's just a matter of taking the bold step, taking the risks, and believing in yourself, understanding what you're doing. We believe that our technology will not fly from anywhere. We will have to create it by ourselves, or we have to facilitate it. We have to influence it. It will not drop on our laps. So, it's still there. The problem of financial stuff is still there. I mean, for integrated position, I believe that we should have actually scaled beyond this. If there is money, but it will always be there. But if you don't actually give up, I think I'm speaking from experience myself, and I'm motivating myself. If you don't give up, the funds will come. This will change. So I would actually say that.
Yeah. Oh, that's great. That's great.
Yeah. Okay. This is the last statement. If GPS is the most in robotics, what happens when it's to be used in livestock? I think I've actually asked this question. Really, he just made it a practical, from a practical perspective. So, Dr. Kenny, I think you want to comment on that, because robotics is not only about GNSS or GPS. It's not only about that.
Right. Yes. So GPS or GNSS is not a must in robotics. And maybe maybe to qualify my understanding of your comment, is GPS a must for auto guidance systems? Because in robotics is broader than what guidance that you need through GPS. Like we talked about, you don't need to rely on only GPS. GPS is entirely unreliable indoors, and there are many scenarios where you need to do things indoors. So there are other ways, I think we touched on a bit earlier, other ways of enabling localization or positioning of your system indoors where there's no access to GPS. And so, yes, that would be a scenario where you have, a controlled environment, like you said, with livestock or poultry or whatnot. There are other ways to enable positioning without GPS. So GPS is not a must. GPS is very important because it is very available in open field. Okay, and it's quite reliable, especially when you have proper corrections like RTK or other ways of correcting your GPS information. It is very reliable when you're in open field. All of the people who drive, you all use GPS on apps to navigate from house to work, to place to another place. GPS is accessible everywhere, most places. So that is why it's very common. But it's certainly not a must. There are many ways that you can try to establish positioning, and particularly when you are in GPS, what's called GPS denied environments. So environments that don't have access to GPS. That could be either because you're indoors, or that might be still outdoors, but not in open field, right? Where you have interceptions or interferences from your GPS signals.
Okay. Thank you so much, Dr. Kenechuku. We are actually glad to have you with us today. And guys, I believe you actually enjoyed your time. You are actually exposed and enlightened. That's actually objective. We're not actually here where we want to be, but we're actually on the track. I think that's what we're actually trying to do here. To actually be on the track, to actually be for Precision Field Academy to be that navigation system that can guide you that can guide you on the path.
That's wonderful.
Pun intended, right? So
Yeah, no, actually, and
that,
if I could say something, I think what you said, Mr. Femi, about how we are in the nascent stage of the adoption of these technologies globally. Globally, agricultural robotics and applying AI and IoT in agriculture is globally in the early adoption phase, right? And so, as someone who is getting in this early phase, really puts you on an advantageous positioning. Allows you to be an early adopter, allows you to be sort of a leader as you grow and develop your competencies. There are certainly unique challenges to doing advanced technology solutions in Africa. And so I think being thoughtful about those things, paying attention to feasibility as you scale, like I think just listening to Mr. Femi talk about his own firsthand experience and how, different business models can either aid or hamper your ability to scale in a particular economic climate. So you need to be thoughtful about that, but remain hungry and remain passionate. And what you will find is as you develop more competency, my vision and my intuition about, like I think I showed at the beginning of the talk, right? That what will farming of the future be, right? In 2050, 2060, 2040, my belief is that the application of technology will continue to rise in this field, not only because technology is becoming vastly more accessible, but also because we really need to have more yield and productivity, especially in Africa. So there will be more interest, there will be more funding, there will be more opportunities in making the connection between agriculture, production, and technology, AI and robotics and IoT and whatnot, smart technologies. So this is the season of humble beginnings, and what you want to do is to be persistent, to be focused, so that you build some crucial competencies that will allow you to reap benefits in 5 years, 10 years, when some of these opportunities continue to expand. So I just encourage you to make the most of Precision Field Academy and all the great things that is there, all the great speakers, all the great resources available. Make the very most of them. Make the most of the mentorship by Mr. Femi, who's a pioneer in this space in Nigeria. I wish everyone all the best. It's been a pleasure being here and sharing the little that I know in this space, and hopefully that helps to spark people's thoughts.
yes, it does. Thank you so much again, Dr. Kenechuku. I wanted to say, after this talk and question, I wanted to say, can you give us your last words, advice and all that before you leave? I think you've already done that.
I think I did,
I think you've
yes.
already
I
laid
jumped
that
the gun.
down. That. No,
Oh, there's
no,
actually
no.
there's one
So
more thing I can say,
we
though.
actually appreciate once again, and myself.
There's
Yeah, please
one
go
more
ahead.
thing I can say. And well, this is not really last words. It's more of me providing. Sorry, just give me 1 minute. Providing, showcasing people to an opportunity that might be interesting to them. And so this specific, let me try and share my screen again. I just remember that this might be interesting to some people. Let me see. Yes. All right. So what I want to just share with some of us who might be interested is in this theme of building competency, building experience and exposure. I help run the Pan-African Robotics Competition. It's an annual competition for people at different levels. There's There's opportunities for people at the secondary school level, opportunities for people at the university level, opportunities for people at the, you're a graduate, but you're really interested in robotics and technology and AI. There's different categories. And this year we are focusing on agriculture, right? So we did that same last year and this year. This is an example of an agricultural robot that was developed for the competition we used for last year. And so if you're interested, you can go to the link here. The link is PAIP Robotics. You can just Google search PAIP Robotics, or you can check from the link. It's starting, the registration is ongoing at the moment between now and April, early April. So if it's something that you're interested in doing, I would strongly encourage you to consider participating in, or at least learning more about the Pan-African Robotics Competition. All right, so that's my last word. Mr. Femi, I cannot hear you any longer. Mr. Femi, I can't hear you any longer. Hello? Hello, hello.
Oh.
Hello?
Yeah, I'm actually
Okay.
happy for you to, I mean, seeing that you're actually sharing with the whole. This is actually what we need.
Mm.
Okay.
I think I can hear you. There is the signal is not
Can
very.
you hear me now?
Yes, I can hear you. I think there's a lot of, it's breaking a lot. It's intermittent, but
Yeah. Okay. Can you hear me now?
yes, I can hear you. I can hear. There's a delay, but I think I can hear you.
Oh my
Yes.
God. I think you should be able to hear me now.
Yes, I can hear you. Yes. Can't hear you anymore though. Mr. Femi, I can't hear you. Hello, Mr. Femi. Audio is
Okay.
not.
Yeah. Can you hear me?
Okay, it is coming through now. Yes.
I'll just go ahead. Yeah, truly, we are actually excited to have you. I mean, share with us the wealth of your wisdom, knowledge, and also benefit from the opportunity that you are actually leading with PARC, Pan-African Robotic Competition. So, guys, this is actually an opportunity if you're actually looking forward to developing your capacity and to also showcase your talent in agricultural robotics, you have stuff to please do well to get on. Just check it on Google. You can be able to find uh, PARC, particularly, and you learn more about their works and how you can actually be part of what they do. So once again, we want to actually say thank you to Dr. Kenechuku Mbanisi. So he is the assistant professor at Olin College. Thank you so much for sharing with us today. So, guys, we are coming to the end of the section for today. So tomorrow is actually some practicals already, I think. So some of which we have built, aircraft modeling, part of robotics. Let's say area robots. We are actually doing that, and drone training. So tomorrow we are actually going to we've taught you the basics, how to drone maneuvers, to operate the drone professionally, and considering risks and all of this. So we're going to take it further tomorrow, and I believe that you're going to be able to see what Dr. Kenya has taught us today in action. We are going to be doing autonomous operation for mapping data collection, in particular, how the navigation system, GNSS, is able to guide our drone on a flight plan or path to be able to collect accurate data with precision and best efficiency. So tomorrow, so do not miss that tomorrow if you are actually on the usual site for us to actually meet. At 9 a.m., I need to stress, it starts by 9 a.m. For respective locations. And it's weekend, but it's what we do and all that. So thank you so much for joining us today. I want to say once again, so happy to actually know you. Thank you so much. Great number of us. To inspiring and to actually educate us. I mean, you have actually done that today. You have actually done that. So, guys, without much delay, as we prepare for tomorrow here in Nigeria, so I will be saying goodbye. Lecture series for the incubation program. It's talking to us through very good consultant, innovation to mission, and going to be taking us through leveraging on social media, particularly. Who is going to be wrapping up on Wednesday. I'm going to be bringing to you entrepreneurs from various countries in Africa who are actually using drones as business. So they're going to inspire you. I want to actually, at the end of this program, our success stories, how many people have been inspired to start a business, to create something, to go further with their education. This is our own house. All right. We are not actually getting money from you. We are doing all of this at low or no cost. So our goal is to actually see the next generation of tech-inclined and digitally savvy farmers, providing value, bringing solution, precision agriculture solution into agriculture, particularly African agriculture. So once again, thank you so much. And we'll see you tomorrow. Bye for now.